Good evening, everyone. Welcome back to a new episode 2, by the way, of Masterclass-ish with Aryan. And today we're going to be covering something really, really special, and it's the concept of isotopes. And isotopes, seriously, they have such far-stretching applications that it's hard to even process. And what I'm planning to make with this is essentially a series because the main piece of feedback I got from my first episode, although it got some great traction, which I'm super grateful for, the main feedback I got was make your videos shorter, Aryan. I'm like, okay. I mean, the last one was 40 minutes long, so it makes sense. And who wants to listen to someone ramble on for 40 minutes? Am I right? And second is make your drawings better and your handwriting better so you don't look like a doctor that's prescribing somebody Vicodin. Okay, makes sense too. So I've prepared some really, hopefully understandable drawings that can get this lesson some legs and make people understand better. So now that I've got that, hopefully we can cover what's really just the ingenuity behind how isotopes can be used and all that sort of stuff. Hopefully by the end of this, we can build to concepts like radio dating and understanding how certain isotopes can be detected and traced back and, algorithmically processed to gain some really awesome information that we just wouldn't have been able to get before. And I really believe it's the closest thing we have today to a time machine, right? And you'll see just how awesome it is as I go through this. But before, I get into what an isotope can be used for, how we can, process them, things like that, let's cover what an isotope actually is. Okay, so when we're trying to understand isotopes, a good place to start would be giving it a nice definition, which I think should be the focus of at least this part of the series I'll be making. Isotopes are much, much, much easier understood, take my word for it, when you understand what a simple, plain atom is, right? Hopefully you've heard of an atom in middle school, high school, whatever, but if you still feel kind of rusty on it, I probably won't be explaining it in this video, so I'd encourage you to just look it up for the sake of curiosity, just to understand things better, because really this entire lesson is going to be based off the fact that you know what an atom is. So assuming that everyone still watching knows what an atom is, you probably also know that atoms come in a bunch of different flavors, right? There's all the elements of the periodic table. I think there's 118 now. And right now we're just looking at one of those, which is oxygen, which I'll get to later. But atoms come in different flavors. Well, going one level deeper into that, what determines those flavors? Well, those flavors are determined by a class of particles called subatomic particles. Um, by the way, the word atom was actually determined by the Greek word atomos. The Greeks actually found a way to just thought experiment atoms into existence. They didn't have microscopes. They didn't really have anything. Atomos was actually just a philosophical concept that if you had any object and you just kept cutting it in half and in half and in half and in half forever, what is the smallest particle object thing you would get that still retained the properties of the original object, and you couldn't cut any further? So atomos literally meant indivisible. But now, since we've had better theories than just philosophy, we've had science to show things like this. Now that we have better theories, we've actually seen that the atom can actually be divided further, and that's actually where subatomic particles come from. You've probably heard of the proton, positively charged, the neutron has no charge at all, and the electrons, which orbit around the nucleus, right? Which is just a clump of positively charged and neutrally charged particles, so protons and neutrons, right? As you can see in this diagram, and they're all, living happily, vibrating freely, moving around, doing atom things. Great. So we have these subatomic particles. And in fact, if you watch my previous video on atmospheric retention, you'd also know that these subatomic particles have mass to them, right? They have an inherent weight that we can measure, right? And again, how these atoms are determined, their flavor, It's determined by, well, how many specifically protons this atom has, right? Neutrons and electrons are still important, right? Neutrons are just important in determining the atom's mass. Electrons are important in determining the atom's charge, but what determines the identity of the atom itself is the proton, right? Those things living in the nucleus that have a positive charge. So where do we go from here? Well, the key insight, just like I said earlier, is to understand that these subatomic particles have mass. And to be more exact on that point, we measure this mass on the molecular scale with a different type of unit called atomic units. And protons and neutrons, in fact, we count them each as having one atomic unit of weight. Okay, so for each one of those in an atom, we would just, add one to the tally and you get your atomic weight. And in fact, electrons, they're just so light that we ignore them entirely. They're just some exceedingly, exceedingly small fraction of one. They're like one in almost 2,000th of the weight of a proton or a neutron. So we just don't count them at all. It's like going on a weighing machine and then cutting off your hair and then expecting that you're going to be any lighter. I mean, you are technically, but it's so small of a difference that it really doesn't make sense to count it. And so really what we do is we just add protons and neutrons and we get a satisfyingly accurate measurement for what an atom's weight is. And you can even run that same calculation for an entire molecule and figure out what its weight is, right? You just run the process over and over. So I'll give you an example of that in real life. Let's look at an oxygen atom. If you run through the periodic table, maybe they went over the song in high school, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Oxygen is number 8 in the periodic table if you just look at it in the order. And if you're really observant, you'll see that the number of protons is another determinant of an element's order on the periodic table. So if it has 8 protons, it'll be number 8 on the periodic table. You could carry that out throughout the whole table. So if we look specifically into oxygen, if you look at, well, the most common form of oxygen, we just label it as O in terms of its shorthand for how we describe the element. The most common types of oxygen, and really the most common types of elements in general, they tend to be stable and very functional if they have the same number of neutrons as protons. And you can see that here, 8 protons, 8 neutrons. And as I said, each of these things counts for 1 atomic mass. You get a mass of 16 atomic units for a regular atom of oxygen. And by regular, I mean the most abundant form of oxygen we see. But there are actually less abundant forms of oxygen. How? Well, if you define an atom by the number of protons that it has in it, and the electrons really don't do anything to its mass, well, couldn't you get the same type of atom and just change its weight with neutrons and then actually have 2 different atoms, but they're actually the same? They have the same identity, but they have 2 different masses, right? You can preserve identity while changing mass. How are you going to do that? You're going to do that by changing the number of neutrons in an atom. And although it's more rare, that's exactly what an isotope is. Surprisingly enough, that's literally all an isotope is. It's another version of just your plain old regular atom. It finds a way to maintain its identity. Again, because that identity is defined by the number of protons, it maintains the same number of protons, but it changes the number of neutrons, right? It usually adds a couple more neutrons into the mix, and then it just gets the same element, but slightly heavier, all right? And if you look at it in the example of oxygen, right? Oxygen is the 8th element on the periodic table, right? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. It's number 8, okay? And if you're observant, you also see that the number of protons an element has is something that completely determines where it's going to fall on the periodic table. Oxygen has, just as you'd expect, 8 protons, and usually the most stable configurations of atoms, and usually what decides what the most abundant form of that atom is going to be, is it has the same number of neutrons as it does protons, and you will see that pattern going over here. 8 protons, 8 neutrons, and you'll see that for any other element, right? 10 protons, 10 neutrons. Sometimes it might be different, right? It might be 13 protons, 14 neutrons, but they're almost always the same, right? And those configurations tend to be stable, and that's why they tend to just persist more in the long term in our environment, and oxygen is no exception of that. But if you look at this, when we have oxygen with a atomic mass of 18, this leaves us with oxygen 18, and I mean, it's not surprising either. The main convention is to just put the 18 or whatever the new mass of this isotope is just on top and then put the element over here. And by the way, you can have multiple different isotopes of this same element, right? Cadmium is a really good example. It has like 12 different isotopes with all different masses, all of which are controlled by one lever, which again is changing the number of neutrons in the substance. Hopefully, as we go on, now that you understand what an isotope is, you will be able to apply these concepts and intuitively grasp how isotopes can be used, how this difference in mass, which is, the cornerstone for all the science that we do today with isotopes, how that difference in mass can allow us to do all these things. That, my friends, is the introduction to the isotope. Hopefully, I'll see you on the next episode of Masterclass Ish with Aryan. See you next time.